Okay, so welcome to Lecture 20 of the class. And today I'm having a little bit of a trouble with the video resolution in this room. So we have a relatively small screen to display on, and I'm capturing from this screen. So I'm not sure how the results are going to look. If anyone had looked at the YouTube video from the last lecture, you noticed that the first hour or so the screen was cropped. Something funny is going on with Mavericks and the video resolution. So in any event, hopefully that's resolved now. So today, what we're going to do is talk a bit more about the Gaussian channel and Bandlimited case, and then analyze the case of parallel channels. And in doing so, we'll review a bit of optimization in Lagrangian duality theory in a way that I hope everybody will enjoy. So with regard to what we should be reading today, this is drawing from chapter 9 in our book. I'm also drawing from chapter 5 of the Boyd and Van Berger's convex optimization book. And also, like I said last time, I'm assuming that everyone has read all previous readings from the first 18 lectures from the previous class. And there's not yet any homework, so we're going to be very happy. So again, this is an announcement. So office hours on Mondays from 3:30 to 4:30, except for, there's a current exception, which is January 13th. If I can do makeup office hours if you want. Either I can schedule one with you, or again, as usual, I'm happy to Skype or Google Hangout or something else. Canvas, the Canvas discussion area, I tried it last quarter and it just didn't work out very well. I think we successfully were able to get an inferior quality voice conversation going, which ultimately made no sense given the high quality of Skype and Google Hangouts. So just some review. So again, just like last quarter, almost every slide, or most every slide, there might be one or two exceptions, but every slide in this review section up here comes from a previous lecture. Okay? So all this stuff, which is review, you will find it's a duplicate, guaranteed, or almost guaranteed. So here's our Gaussian channel again, and this is the channel that we've been analyzing, where we have an input, which is basically x, which is corrupted by some Gaussian noise. It's additive Gaussian noise, and we get some output. And for each use of the channel, we send a number, it gets corrupted by noise, and we receive a number on the receiving side. And the question is, what's the capacity of this channel? And we saw last time that if the noise power, which is sigma squared, is 0, then the capacity is clearly infinite, because we can send any real number, and any real number can be infinitely long. And similarly, we saw that even if the noise power is greater than 0, we can also send effectively any real number, because we can just make the signal power unboundedly large. And so it makes most sense, it only makes practical and mathematically interesting sense to put a power constraint on the input, which is what we did. And there are a number of different forms of power constraints that we could use. The one that we're analyzing in this class is the case where the average power, which is the power, the average signal energy essentially is upper bounded by some constant p. P is a constant. And that's sort of given beforehand. And this is an estimation of course, the expected value x squared. There are other methods that could be used, but we're using this one. Okay. So then we define the notion of a capacity, of an information capacity, which, similar to like we did last quarter, wasn't yet something that put a limit on how much information we can communicate per channel use. In other words, we don't yet know if this is a bound on our rate. But as you can probably guess, it will be a bound on our rate. And the way we define it is very similar to how we defined the capacity for the discrete channel, except that there's a constraint now, where the constraint says that, well, we're maximizing overall P, but the constraint is that the power constraint must be satisfied. So we're not interested in distributions that exceed our power usage constraints. And in order to compute the capacity, what do? Well, we do the same trick again that I've now said many, many times, is that we upper bound the mutual information, and then we find an achieving distribution P. And that gives us the computation of the capacity. And again, that achieving distribution P of x may or may not be the one that we actually code with. It's not necessarily unique. There's no guarantee that equation 20.5 has a unique solution. It's just that there is some solution. And so this was the upper bound, which was this form. And I think I mentioned something that was potentially important here, was that this isn't the upper bound. This thing here is basically equal to the mutual information, which doesn't mean the mutual information can be negative. It just means that this quantity, h of y minus h of z, in the case when y is equal to x plus z, can't be negative. It's just it puts a bound on that quantity. But we know the mutual information, even in the continuous case, can't be negative. So that's basically this point right here. Pay attention to this inequality. Okay, so then we said, well, we know from our maximum entropy results for Gaussians that Gaussians achieve the maximum entropy. Z here is already Gaussianly distributed. Why, we don't know, but we know that we can upper bound the entropy by a Gaussian having exactly the same signal power, which is P plus sigma squared. Because remember, x and z are independent, so the power is just the sum of the powers, so P plus sigma squared. So that gives us an upper bound on the mutual information, which then we can write as 1/2 log plus the signal to noise ratio. And to actually achieve the upper bound, we ensure that y is Gaussian. And that can be the case by making sure that x is Gaussian, because sums of Gaussians are Gaussians. And so then we get our result, which is that the capacity is equal to 1/2 of log plus 1/2 of log of 1 plus the signal to noise ratio, which is very, very satisfying because it says, the ratio of the signal power to the noise power is exactly the thing that determines how many bits per channel we can use. It doesn't say anything about the absolute value of the signal power or the absolute value of the noise power. It just says it's the ratio, the signal-noise ratio. So if the signal is strongly high, if there's a very, very strong signal, if it's high, if it's much above the noise power, then we can communicate noise-free. And that's the theorem that we have to prove, or at least that's what the definition is. That's what we will be proving. Right now, again, this is just the solution to the optimization problem. So, and again, without a power constraint, the capacity is infinite. So I thought I'd do a fun, simple example for those people who are interested in audio processing. Raise your hand if you care about audio processing. So I'd say about 20% of you. You might wonder how I'm able to so accurately estimate percentage of students who raise their hand in this room. And that is a secret which I will withhold from you. But I can say, in fact, with certitude, that 20% of you are interested in audio processing, which isn't zero. So therefore, I think this is a useful example. So this is something that you've taken from your signal processing classes. Here at UW, it would be in, say, something like 341 or 518 or 519. You use this quite a bit, which is that if you've got a band-limited time signal, x of t, oops, I don't want to cross it out, I want to highlight it. And you have this critical point, Fc, such that there's no signal energy above this point. It's a band-limited signal. Then as long as we sample at a rate of 1 over tau is the rate, greater than 2 times f of c, which is the Nyquist rate, then we have perfect reconstruction, and we get our sampled signal in this following way, where essentially every tau seconds we just look at a sample. Tau, again, is the sampling period. So that's basically fundamental Nyquist theorem. But what, at least when I used to teach 518, which was ages ago at this point. We didn't spend too much time on the analysis of the quantization, because when you're actually representing sampled signals on a computer, each number is represented with a certain number of bits. Right? If you're using audio, most audio, what we call PCM sampled quantized audio, it's CD quality. So CD quality doesn't really make that much sense anymore because very few people listen to CDs, compact discs. Everybody these days listens to lower quality MP3 files or something similar. But back in the day when CDs came out, it was the first sort of widespread use digital audio format. And that was basically 44.1 kilohertz sampling rate, which means that you get about 20 kilohertz of bandwidth, assuming a not too stringent requirement on your low-pass filter. And secondly, you had 16 bits per sample, right, which was deemed good enough. Although we can talk about that. If you go back and look at the quality of the CDs that were produced in the mid-'80s, they're much, much worse than even the ones that are produced today. But that's for a different reason. But in any event, the question is, this sampling theorem, sampling theorem, doesn't say anything about what kind of loss that you would get by using 16 bits per sample. Obviously, if you use 1 bit per sample, that's really bad. If you use 24 bits per sample, which is what professional recording studios use, that's really good. If you use 16 bits per sample, that's somewhere in between. Now the question is, how do we analyze this? We didn't analyze this in 518. I don't know, has anyone taken 518 recently? Is that analyze the quantization? Maybe not. So in information theory, we have now the tools that we can do that. Because this turns out to be well modeled by a Gaussian channel. So quantization error, what essentially happens is the following. We have this original signal. Let's draw the original signal in green. So it's a continuous valued signal. Right? The first thing that we do is that we sample it. Right? So we essentially look at it every, we're using cap t here as the period. But basically, you get the idea. Like every cap t seconds, you take a picture of it. And if you were to take a picture of it, let's zoom in a little bit on this. If you were to take a picture of it, you get an exact value. You get a value right, let's say here. But which is what the Nyquist theorem applies to. It's basically when you have essentially infinite resolution, you have an infinite number of bits to represent each voltage value, or whatever the signal is actually representing. When we have a quantization error, essentially we know, basically we have discrete time and discrete voltage, or discrete value. And that basically says that we also have to quantize in the vertical axis as well. So then zooming back in on that point, it says that rather than having this blue value, we have maybe this cyan value here. And so this difference, this gap here, constitutes quantization error. Now obviously the quantization error isn't bounded, because if it gets too big, then you march down to the next quanta. But on the other hand, it actually turns out that these errors, if you look at them, are actually quite well modeled by a Gaussian noise source. They're obviously not really Gaussian, only, if anything, because they're restricted to be between plus and minus 1 quanta away from the true value. But on the other hand, they are kind of bell-shaped, and most of the values are kind of close to the actual value. And so if you're willing to accept that it's reasonable to model these errors with a Gaussian noise source, then we can essentially represent these quantized values to say that, okay, well, here's now our sampled signal. X is the continuous time signal here, this thing. Here's the sampling process, n times tau. And here's a Gaussian noise, additive Gaussian noise being added to every sample, which gives us this, and then which gives us this. So this is really our representation of the discrete time, discrete voltage signal. Okay. So the question is, is this a Gaussian noise source? I mean, is this a Gaussian channel? And you can see if this, under the model of equation 20.2, this is clearly a Gaussian channel, right? We've got a value x, we've got some noise, which is z, and we add it together, and we get a resulting quantized value. Now, when you're using B bits, so B might be 16 in compact disc quality audio. When you're using B bits, then you have 2 to the B different possible values you can represent. Now, one of the, I remember this very well back in the 80s when CDs came out, and there was enormous debate in the community, in the professional audio community, about the quality of CD and whether or not the dynamic range, which is the ratio between the loudest possible sound and the smallest sound before you hit the noise floor, whether or not it was better than LPs, records, analog scratches in vinyl. And there was, at that time, analysis that said that you have about 96 dB of signal-noise ratio on a compact disc, in theory. And so what we can do is we can use, and they were implicitly using, in fact probably explicitly using, although they never mentioned it, they were using Shannon's capacity computation of the Gaussian channel in achieving their result of 96 dB signal-noise ratio. So how do you get this? And then the other thing you get, which is what the title, which is part of the title of this slide, which is that each additional bit you get is 6 dB. You get additional 6 dB, 6.02 dB of signal-noise ratio for each additional bit. So if you went from 16 bits per sample to 17 bits per sample, you'd have about 102 dB of signal-noise ratio. So when you go to 24 bits per sample, which is professional audio, then you have many more, much higher. Now, you might think, why would you need such a large dynamic range? So if you have an additional 24 bits, that's 8 more bits, that's 8 times 6 plus 96, much larger than the dynamic and the signal-noise ratio of the human hearing, or most mammalian hearing systems. And given that we are mammals, why would we need such a high signal-noise ratio? But that is really a question for professional audio. But on the other hand, I'm willing to answer that question if you're interested, but at least all 20% of you. But what we're going to do here is we want to get this 6 dB signal-noise ratio per bit result from the Shannon capacity. So here's the capacity, the thing that we just derived. So let's plug in B is equal to 16. So 16 is the number of bits per sample. And so we identify, 16 bits per sample gives us our capacity. Each audio sample can hold 16 bits of use. So it's kind of like a Gaussian channel. We take a real voltage value, but we are only limited. We're limited by the 16 bits that we've got, which is the number of bits per sample. So the capacity is equal to 16. And we equate 16 with Shannon's formula in here. Okay, then let's just solve for the signal-to-noise ratio. So a little bit of algebra, we get signal-noise ratio is equal to 2 to the 32. And then let's use the standard decibel measure of signal-noise ratio. Since the signal-noise ratio is in terms of power, we use 10 log 10 rather than 20 log 10. So 10 log 10 SNR gets us, when SNR is 2 to the 32, gets us 96.33 dBs of signal-noise ratio. And then, well, how many decibels per bit do we have? The way we get that is we divide by 16. So 96 divided by 16 gives us our 6 dB per bit. So, therefore, each additional bit gives you an additional roughly 6 dB. And that's where that formula, that number comes from. Now, at the time, I mean, to understand this as a layperson, or even as an audio professional, without actually understanding signal processing and the Nyquist sampling theorem, and also understanding information theory, and all of the stuff that you've now gone through last quarter and the beginning of this quarter to understand the capacity, the concept of capacity, the concept of information, the concept of Gaussian channel and maximum entropy, and all these other things in order to actually get this formula, 20.3, that would be a huge investment of time just to understand one little thing. But you now know it. And so next time you're at home with your family and you're listening to music, and somebody puts on a compact disc, and if the topic happens to arise, how much signal-to-noise ratio does this compact disc have? You shall know the answer. Or at least I hope you will. Okay. All right, so let's now get a little bit more into Shannon's second theorem, but applied to the Gaussian channel. Now, I mean, the similarity between the discrete and the continuous case is so great that I'm actually not going to go into it in great detail. We should just instead go back to lectures 14 and 15 from last quarter, and we're just going to really, in some sense, outline the kinds of things that you do here, but they're really the same. They mirror image all of that stuff, and there isn't really much in the way of differences, except really in terms of this power constraint, which is the real difference. So we have the notion of an MN code, which in this case has a power constraint, which consists of an index set, like we had last quarter, an encoding function, which gives us a set of code words, and each of the code words must have this power constraint. Each code word consists of n real numbers, because remember, we're using the channel n times. And then we have a decoding function, which basically takes what was received and maps it back to an integer, and we have the notion of an error, which is that if the decoding function applied to what was received is different than the original index that was sent, then we have an error. The notion of rate is the same. It's basically the total number of bits that we need to specify one of the m messages, which is log m, the total number of bits divided by the number of channel uses. So the rate is again specified in number of bits per channel use. And this is, again, I was, at the end of last quarter, there were some questions about rate. So there are several discussions of rate in last quarter. So everyone should be, at this point, extraordinarily familiar with the notion of how we're using rate. There's not time. Rate is typically something for unit time. This is bits per channel use. And you can turn it into a time rate if you are using the channel some number of times per time, per unit time. But here we're really talking about a rate in terms of bits per channel use. That's really important to understand. And we have the notion of an achievability of a rate. So basically, again, achievability means our notion doesn't say that for any given rate you're guaranteed to have zero error. But the notion of rate basically says that if you use the channel n times, and if you increase n, the error decreases exponentially fast. And in particular, it says a rate is achievable if there exists a sequence of mn codes, or 2 to the n codes, that on the one hand satisfy the power constraint, and so this is what's different. We have to satisfy the power constraint, and secondly, the error has to go to 0. And then the capacity of a Gaussian channel. So remember, we have the capacity of the optimization problem, the information capacity, which is optimization, and we have the capacity of the Gaussian channel, which is the supremum of the achievable rates, or the max, if you will. Try to have that. Okay. And so Shannon's second theorem then equates this capacity with the other capacity. So again, this is a delta, a proof delta. So you should look at lectures 14 or 15 from last quarter, which you can get to. You can even watch the lectures. You know what? I'm wondering what's going to happen if people only watch the lectures. This will be an interesting thing. I will be lecturing to myself. But I will do that if that's what it comes to. So, so the capacity of a Gaussian channel with power constraints. This is the theorem that equates the information capacity to the supremum of the achievable rates. And it basically says what we're not surprised to hear, which is that the capacity has this form. Again, where really it depends entirely on the signal-to-noise ratio. So we have two choices. If we want to send more information, we reduce the noise or increase the power. So So here's just a proof sketch, and I'm going to go through this fairly quickly. Again, this is a sketch that mimics it. So we have a typical set. We use typical set theory. That's one way of proving it. And the typical set has, this is the volume. It's 2 to the n h of x. And there's some epsilon fix-ups, which go to 0. And you have a conditional typical y volume, which is 2 to the y, 2 to the n y given x, which, because it's a Gaussian channel, really is just 2 to the n h of z, where z is the noise. And we have the unconditional y set, which has volume 2 to the hy, 2 to the nhy. We have that the entropy of h of z is given using that formula, which follows because z is a Gaussian. And we have the entropy of h of y is upper bounded by this formula. And this formula follows because of the fact that it's additive Gaussian noise and it's independent Gaussian noise. Okay? And it's also because the Gaussian is the maximum entropy distribution with variance p plus sigma squared. So then we compute these ratios, which is exactly what we sort of more formally did last quarter. It's the ratio of total available volume to sort of x conditional volume. And so the total available volume is in the numerator, which is this, and the x conditional volume is the volume of the noise. And so we get this part here. Can everybody see these equations? Okay. And then when we cancel out all of the stuff, we've got that this is the number of small volumes that can fit into a big volume approximately. And then another way of writing it is this way. So again, it's very related to the signal-to-noise ratio. And you know, the assumption here is that there isn't any overlap in volume. So I mean, obviously, if we were to have the sort of x conditional volumes overlap with each other, we could fit more in, but that would lead to an error. So the whole point is that we can't have them overlap, otherwise we're going to get error. And so we get this rate. We can just essentially equate this, and we get that this is the rate. Again, 1/2 log of 1 plus the signal-noise ratio. And we can actually write this. If everything happens to be jointly Gaussian IID, so in other words, we're using the channel n times, right? And if all of the noise sources have the same noise variance, and all of the channel uses, x's, all have the same channel variance, it's a big giant joint IID Gaussian. Right? And in such case, the volumes are basically spheres. Okay? And so we can relate the sphere volume to get the actual radius in n dimensions. So this is just the formula for the volume of an n-dimensional sphere with radius r. Okay, so it's n dimensions, radius r. And then what we're going to do is we're going to equate that with this noise volume, and which is equal to this, to solve for the radius. And there's our solution for the radius. I don't know if this is useful enough, but I thought it would be informative. And so then this essentially becomes like a sphere or a bin packing kind of problem. How many small spheres of radius r sigma squared fit into a large sphere of radius r p plus sigma squared? And again, it's where we solve this radius in exactly the analogous way that we had solved this one, except that we use just a different power. So the idea, again, like last quarter, is that as long as these guys don't overlap, you know, then the ratio gives us the bound, and so we get all these spheres fitting in here and stuff. There's some really nice pictures from last quarter. If you're interested in seeing really nice pictures, then look at lectures 14 and 15 from last quarter. So here's a couple of additional deltas. So this is to show so that basically, that version of the proof shows that we can achieve the probability goes to 0, then the rate is less than capacity. Here we basically need to show that if the rate is less capacity, then there exists a code, which is the converse of the theorem. And again, we're just going to do the step that's different. And again, the way this was done is to, again, use a random code generation. You do random code generation, like in the discrete case. But in this case, we generate random code words from Gaussians that satisfy the power constraint. And the power constraint has, again, like we saw before, an epsilon, but now the epsilon is something that's being subtracted from the power constraint. Now, since it's a Gaussian, we have an additional source of possible error. And another error that we have now, other than the existing, we had like 3 different types of errors last time. And now we have an additional source of error, which is, well, what happens if the code word exceeds the power constraint, which is not something that is impossible. But by the weak law of large numbers, since p is equal to the average, as n goes to infinity, the probability of that error happening goes also to 0. Probability of E0 goes to 0 as n gets large. And so therefore, in the limit, asymptotically, nothing really changes. It's an additional, again, by the union bound, it's an additional source of error. The union bound makes it such that we can add E0 to the other errors, and we essentially ignore any dependence. And each one of these individual terms in this upper bound of the errors, each goes to 0 when n gets big. This last one, again, by the weak law of large numbers, says that this power constraint violation error, this guy, this is the power constraint violation error, goes to 0 as well. So again, this is a proof delta, and if you don't remember the proof from last time, this won't make any sense. But I don't think it doesn't make sense to go through the whole thing. Okay, are there any questions on this topic, other than more information about the previous proof, which is, like I said, something that I wasn't planning to go over. Can you raise your hand if you understood this argument? Okay, so 100% of you understood it. So I'm really good at estimating percentages. Let's talk about the band-limited case, because in real Gaussian channels, it's not the case that one can have unlimited spectral bandwidth. And so what does it mean to not have unlimited spectral bandwidth? It means that in some sense there's a bandpass filter being applied to the channel. And so let's say that H is our bandpass filter, and there's some critical value, W, which says that the filter has 0 response outside of that band. This is again the Fourier transform. And so if a way of modeling this is via convolution. I mean, we're assuming an LTI, a linear time invariant system, in the sense of that you can actually describe it with convolution, the process using convolution in this equation. And the idea is that you're sort of, it's a time signal, but you're low-pass filtering it. Okay, so you have no chance of sending any information whose variation exceeds the spectral crop of the low-pass filter. In this particular case, let's just assume it's an ideal bandpass low-pass filter. Sorry. Basic bandpass. Well, I mean, I guess this could be a bandpass or a low-pass filter. I said low-pass before. Here it says bandpass, but let's just assume it's a low-pass. Now the question is, how does this band limitation, W, change our capacity? What does intuition tell us? If we make W smaller, is that going to increase our capacity? It should decrease it, right? So, and if we make it bigger, it should not decrease it. Right? Or really, it should be, if we make it smaller, it should not increase it. And if we make it smaller, it should not increase it. That's technically the correct way of saying that. And so, in general, if the signal is band limited to W, so how many samples are needed? In general, again, from Nyquist's theorem, you need about 2 W samples per second. You have 2 W degrees of freedom. Right? No, any more doesn't buy you anything. This is roughly. One sample every, this is again the sampling rate, 1 over 2W, where W is the bandwidth. And again, this is obviously not in radian frequency, this is in just regular old frequency, this is the period. And this again comes from Nyquist's theorem that I'm assuming everybody knows. And we're also going to assume that the signal is short, or it's not unboundedly long. So the signal is going to be both time and band limited. And so the signal is going to be limited to length cap t and band limited to cap w, which means that we can describe the signal effectively with vanishingly small error if we use roughly at least 2 WT samples. So we need 2 WT channel uses. And another way of describing this is to say, during reconstruction, when we interpolate the samples, it's such that if we were to, for example, use the right basis function, so this is sort of a reconstruction error, that the signal x of t can be accurately represented via this interpolated reconstruction. Okay. So this is the residual error here, and it's easy to show, or there's lots of different ways of doing it, but you can show that this residual error is very, very small if we use at least 2 WT coefficients. So the alphas correspond to the samples. This is something, it was described first in Gallagher in this context, in the information theory context. So basically, we've got a Gaussian channel, but now the bandwidth is limited. We don't have unbounded bandwidth. Now the noise, we need to talk about the spectral density of the noise. Let's assume that the spectral density is sigma squared halves, units of watts per hertz. Sorry, excuse me, I have a bit of a cold. So the noise power is going to be essentially the spectral density times the total bandwidth, which is 2W, so that this is going to be the final noise power, sigma squared W. And the spectral density of that. The overall energy then multiplies that by time, right? So this is the noise power multiplied by time when we get the energy. It's energy, it's power is energy per unit of time. So this becomes the total energy of the noise over t seconds. And each noise sample has a variance, which is the power, the energy, divided by the number of samples. So the energy per sample is going to be sigma squared over 2. So this is the variance of the noise. So then given x, z is, it's a Gaussian channel. So this is also z. It has this type of distribution. So now this particular form that we're describing it in is sigma squared over 2 times I, which is the identity matrix. So we're talking about all 2 WT samples simultaneously in a big independent joint Gaussian. So it's a Gaussian with a covariance, with a diagonal covariance matrix. In fact, it's a spherical covariance matrix because all of the diagonal entries are identical. So it's an IID assumption of the noise. Okay. So then, what happens next? Well, thanks to it being spherical, it's also ball-shaped, which is another name for sphere. So the signal power is, again, we have 2 WT samples, and we have T times P, which is the energy. So again, we have the energy of the signal divided by the total number of samples. So the signal power per sample is P over 2W. Which is this. And so the noise power is sigma squared. And so then from this we can actually get the signal-to-noise ratio, which is P, the signal-to-noise ratio is going to be P over 2W divided by sigma squared over W, which can be written as just P over sigma squared W. And so basically then the capacity becomes 1/2 log of 1 plus P over sigma squared W, bits per sample. So now what has this done? What these simple arithmetic expressions have done is given us an expression of the capacity of the Gaussian channel under the band limitation W in terms of the signal power, P, which is in the numerator, the noise energy per sample, sigma squared, the thing that matters, and the bandwidth. Okay. Of the channel. But then lastly, we're using 2W samples per second. So this is in terms of bits per sample, but this is the final capacity is in terms of bits per second. Because remember, when we're talking about a sampling rate, there's time involved in this. Right? So it's interesting that if we just look at it in terms of bits per sample, what the bandwidth does is actually reduce the capacity in terms of the number of bits per sample. But overall, in terms of bits per unit time, we have to multiply it by everything by 2W, and so we get this formula here. So it's W, which is the bandwidth, times log of 1 plus P over sigma squared W. So that is this famous formula that you see all over the place, or in classic, famous classic information theory formula. Okay, so what does this mean? Well, on one hand, the bits per sample is going down with increased W, but on the other hand, because this is in the denominator inside of the log, W is increasing, and so therefore, as we increase W, the capacity is going to increase. So we can increase the capacity either by increasing the bandwidth, W, increasing the power, P, or decreasing the noise variance, sigma, per sample. So we have these three knobs we can tune in a Gaussian channel to affect the capacity. And again, the capacity is, again, this sort of bound on how many bits we can use error-free. And here's the function. Here it is. So this is plotting C. The capacity is a function of W for fixed sigma squared. So the one thing to note is that if you increase the bandwidth unboundedly, then it saturates. You have the saturation point here, the saturation value. So even if you have infinite bandwidth, this is the final capacity. P over sigma squared value. The other thing to note is that if there's sort of this rapid rising period here, and then this more slowly rising period here, and the point, in some sense, P over sigma squared, is that critical point where it moves between these two regions. If I talk this softly, I don't think anyone's going to hear me on YouTube, so maybe I should stand closer to the microphone. Actually, if anyone knows of a good lapel microphone, that I think they're called lapels, the ones that you clip on, then no matter where I'm standing, you'll be able to hear me. But I couldn't find one that would easily plug into a laptop. I'm sure it exists. Okay, anyway, any questions on this? Question? What? Shoot.
No.
Oh, no questions.
Sounds good.
Sounds good. Okay. Okay, so next thing we're going to do is parallel channel, but I mean, we might as well take a short break now. So let's take a short break, maybe a 3-minute break, and then start talking about parallel channels. Okay, so let's get started. So I apologize first of all for the quality of this figure, or actually maybe I should say I used the natural writing font for this particular figure. Basically, we're given n independent Gaussian channels. So it's just basically a Gaussian channel repeated n times, and we can write it either in this fashion, where we do have in fact n independent Gaussian channels, or we can write it one sort of vector Gaussian channel, where the input is a vector, the noise is a vector, and the output is a vector, where the noise profile is characterized by this Gaussian. And again, the Gaussian's got it's a diagonal covariance Gaussian. So these are the only non-zero entries, which is the one that counts. Everything else is zero along the diagonal. Okay. So and we're interested in understanding the capacity of this. Now, on the one hand, first of all, let's characterize or let's fully define this problem. The noises are uncorrelated. They're independent and uncorrelated. So J is independent of Zi for I not equal to J. And if we're interested in just the capacity of this, it's actually fairly trivial. In fact, this was related to the final exam that we gave last quarter, where if we're using one channel at a time, the capacity is going to be equal to log of the sum of 2 to the c's. To each of the capacity, where Ci is the capacity of each of the channels. And if we can use the channels simultaneously, then we just sum the capacities. It depends. The capacity does increase if we can use the channel one at a time. Because essentially the number of symbols, the number of bits per joint channel we can do increases, but it only increases as the log of the sum of the two capacities. So this is somewhat, at this point, a trivial result, because that doesn't mean that our final exam last quarter was trivial. It only means that we know it now, and anything we know is trivial, right? That's the mathematical dogma that once you know something, you just say clearly, or it can be trivially shown. And no matter how many times people express frustration by such expressions, people continue to write such expressions, including me. I've written that too, clearly. But in any event, clearly, this is a trivial problem. It can be shown trivially that this is true. What is less trivial because we haven't done it yet, but only not trivial because we haven't done it yet, is what to do if there's a common power constraint amongst the channels. So what do we mean by that? Well, we mean that the powers, we may be flexible as to which channel we use which power on, but we have a common power constraint, meaning that the sums of the signal powers of each of the uses can't exceed P. So this kind of makes sense, right? Because it sort of says, well, my total energy is bounded, and if I use it, I'll use it n times, and then n times P is the energy, and then I sort of have unlimited energy. There might be additional individual constraints. Like, for example, you might have this offers a constraint. If you think of this as a vector or as a polytope, let's see if this will work here. You could think of this as having, like, if this is P1 and this is P2, what this constraint does, oh shoot, what is happening? Oh, you know what this is? This is someone on our network attempting to communicate to our air server. Someone in this building somewhere is saying, oh, I'm going to connect to this. I always find this very funny because what I do when we do this on public networks is that, so this is effectively an Apple TV protocol running on a laptop. When you connect your laptop to Apple TV, what you're doing is you're allowing your display to be displayed on somebody else's laptop, and you have no idea who. You took my speech recognition class. Remember when we started hearing music? So I've since become a little bit more wise about that, and I've added this on-screen password. So you here being in this room could know by if you connected your iPhones or something, to the screen, you would be prompted by this password, and if you would have entered that password, you would be able to show your iPhone on this screen right now. Please don't do it. But others can't because they don't see the on-screen password. So that's what's going on there. So, and this is something that if I do a private network won't happen. So I don't know why I'm telling you this, but just ignore that and just forget about what I just said because it has nothing to do with the topic. But what does have to do with the topic is additional power constraints that we might have. Let's zoom into this little polyhedral constraint on the power vector. So basically the one, this sort of says that P1, this is sort of the P1 plus P2 is less than or equal to P. That's that constraint. Obviously the powers can be negative. But you might have other constraints as well. Like you might say, oh, I don't want P2 and P1 to be too big. And so therefore you get like a power constraint that looks something more akin to something like this. You know. So this, whoops, not this. Would be this. This should be a polytope associated with the constraints on the power. But we're not really going to talk about these other things. What we're going to do is just assume that we just have one constraint, which is this one down here. It's already sufficient. But I mean, actually, the analysis for doing the polyhedral constraint depends on the polytope, of course, but the analysis actually doesn't become too different. So everybody understand we've got a constraint on the power, on the sum. It's not necessarily the most realistic one because we might do something else. Okay, so our optimization problem is to compute the maximum capacity. And what essentially we're going to spend the rest of today talking about is how to solve equation 20.23. And again, this is a little bit going to stray from what traditionally is in information theory because we're going to talk a little bit about convex optimization, things like that. But we want to understand why this works. So we're interested in the joint distribution of x1 of xk such that the expected value according to the joint distribution doesn't exceed the power, which is this guy at the bottom. Could you raise your hand if you've taken mine and Fazil's convex optimization course? Okay, so some of this will be a little bit review. Raise your hand if you think you're an expert on duality. Okay, so maybe this will be useful. It will be useful for all 100% of you and 40% of you took the course. Again, my impeccable percentage of class estimation abilities have shown themselves. I think if I keep giving these percentages, people will be able to understand how big we are on YouTube. So, actually, I think that already does it. So, actually, no, it doesn't. We'll be able to understand. We're actually, see, people don't realize that we actually have 1,000 people in the room. And exactly multiples of 20% people raise their hand at any time. So now 400 people just raised their hand, right? All right, so what are we going to do? So let's do the same trick we've been doing. We take the mutual information and we sort of are going to upper bound it in this way. So we write it using the chain rule of mutual information for vectors. The entropy of z given x. Again, all of the z's are independent of all of the x's, and so that is easy to just turn into the entropy of z's because they're independent. We got this guy here. Right. And we still have equality everywhere because all of the z's are independent, and when you have independent random variables, the entropy of the set of random variables is equal to the entropy of the sum. So we've got this. So no inequalities yet. Everything's equal. At last, we do make an inequality. We do need an inequality because we use the modular bound on the entropy, which is that the entropy of a vector is upper bounded by the entropy of the sums of the individual, the sum of the entropies of the individual elements of that vector. So that basically gives us this guy here. And that's upper bounded by the capacity. Now, one thing to sort of recognize here is that this is a joint distribution, And because there's a power constraint, we need to optimize it over a joint distribution. It's not, necessarily a priori going to be a distribution that's independent, in the sense that the one that maximizes this quantity necessarily isn't going to be one that's independent. We're not actually requiring it to be independent. We're not saying that the sources are independent. We're just saying that the noises are independent. And so this is not necessarily an equality yet, whatever. And then similarly, once we've got it in this, once we do have this independence, which is down here, we essentially are back to the multiple independently used Gaussian channels, which each have a capacity value, which we know to be this quantity. Okay, and that's an upper bound, right? That's the capacity, so it's an upper bound on the entropy difference. And again, we've got the individual signal noise ratios. Which are these guys. Now, we do have a constraint, however, which is that, well, we have an expression for P, and we also have this constraint, because we're still abiding by our constraint, which is that the sums of the powers equals the power, the overall power P. So, what we want to do then is we want to maximize, we want to find the constraint, we want to maximize this quantity subject to this constraint being held, in order to compute the capacity. And then we need to find an achieving distribution. But just solving this optimization problem is what we want to do. So this is essentially what we're going to talk about, is how do you solve this optimization problem? Because the classic, what we're going to ultimately do is, hopefully by the end of the class, talk about the classic water filling argument that gives you the solution for the parallel channel case under a joint power constraint. And the water filling, in order to understand water filling, you really need to understand the KKT condition. In order to understand the KKT condition, you need to understand duality. So what I could do right now is just skip to the solution, but we're going to spend a lot of time on this. Okay. So, like skipping to the solution, we'll just say, okay, well, let me just form a Lagrangian and solve it and done. Right? But that's not what we're going to do. What we're going to do is step back a minute and steal from Chapter 5 of the Convex Optimization book, which is the chapter on duality, and say, okay, well, we've got a general minimization problem, and this is sort of subject to inequality constraints and inequality constraints. And so F naught is going to be our objective, and F1 through P are going to be functions that parameterize our constraints. And this basically corresponds to any problem you could imagine. In fact, even it's a little bit, with lots of generality, you could just have inequality constraints. But let's just talk about this particular problem, because it's simple to do so. And the question is, how do we solve these kinds of things in general? Well, the first thing that's typically done is you form a Lagrangian and use Lagrange multipliers. So we have a set of Lagrange multipliers, lambda and nu. Okay. Depending on what type of constraint it is, we use either lambda. So we use lambda for the inequality constraints and nu for the equality constraints. I should also mention, this because it's not clear, that we can turn this into a maximization problem by taking negative f naught. And so this sort of captures it. And we can have, this is less than or equal to 0, we turn to greater than or equal to 0 by taking negative f of I, and so on and so forth. So that the negatives, by multiplying by negatives, this is general. I'm not even saying anything about the f's, whether they're convex or anything. This is just a general optimization problem. And then we can define this dual function, g of lambda nu, as taking the infimum of the Lagrangian at the particular point. Infimum over x of lambda nu. So this is a definition. So what we want to do is we want to understand this function, which I just said was the dual function with respect to this original function, and how we can use that dual function to help us solve the final problem, which is this problem up here. The first thing to note is that the that the dual function g is concave in lambda nu. And the reason why is because it's a pointwise minimum over a function that's affine in the arguments of the function. Right? So here's a very simple example. When you think of this as just a function of lambda and nu here, it's basically, we're taking a minimum, and we have a set of possible values of x, which in this case is only 2, it's a or b. But for each value of x, let's take one of them, and so it's f1 of a lambda plus f2 of a nu plus fc. So that's affine, that's just a linear function, or affine function in lambda nu. And then we take the minimum over both, and so that's known to be a concave function, which you can get by, there's one affine function, there's another affine function. You take the minimum of it, which is going to be concave. Polyhedral concave. That's okay. So here's the Lagrangian again, just for reference. So remember, when we take the minimum over x, we've got a concave function. And it's concave irrespective of f's, right? It's always concave. So the dual is always concave, as long as we express it in this way, in terms of Lagrange multipliers. Now, let's assume that lambda is greater than or equal to 0. So if lambda is greater than or equal to 0, then the dual function, which is this, and it's defined again to be the minimum, the infimum of the Lagrangian for each value of lambda nu, is always going to be less than or equal to the optimum value, p opt, which is equal to f of x opt. Now, the reason why this is true is because the optimal value, I think I have a slide. The reason why this is true is because when we take the optimal value, so optimal value is necessarily feasible. So what does feasible mean? Feasible means any value that's feasible must satisfy these constraints. So feasible x means that for I is equal to 1 to m, f of I of x is less than or equal to 0, and for I is equal to 1 through p, h I of x is equal to 0. So, and that this is a whole set of values that are possibly feasible. The optimum of this problem is obviously going to be a feasible one, because we take the optimum subject to the set of constraints. So feasible solutions have the property that fi is no greater than 0, so it's either negative or 0, and also have the property that hi is equal to 0. And so then when you look at the Lagrangian form, this guy here, f opt, has all of this stuff canceled out. Right? Yet if we take the infimum of the Lagrangian for any given value of lambda nu, and if lambda is greater than 0, we've got this part here, which can only be negative, because fi is negative and lambda I is greater than 0. And we have this part here is equal to 0. And so therefore, when we're taking the minimum over x. So therefore, we've got that for all values of the dual function, this is for all lambda and nu, we have g of lambda nu, which is defined in this way, is less than the Lagrangian at the opt value, any lambda nu, which is less than or equal to f opt, because by x being feasible, h is 0, and so nu doesn't matter. And by x being feasible, lambda being greater than 0, f of I is going to be less than 0, so that's only going to decrease it relative to the opt. So this is something that, again, I'm taking from Boyd's book, but essentially you can sort of think of Lagrangian as sort of a soft version of hard constraints. And so here's an expression of something, of an objective that is infinite whenever the constraints are violated. So whenever the constraints, these guys here are indicator functions. So whenever f of I is less than or equal to 0, this whole thing becomes 1 minus 1, which is 0. So it doesn't do anything. Whenever f of I is greater than 0, that's the indicator 0, so we have 1 over 0, which is infinity. So we've got infinite cost. And similarly here, this is an indicator of h being 0. Whenever h is equal to 0, it's 1 minus 1, which is 0. Whenever h is not 0, it's going to be 1 over 0, which is infinity. So this is like a hard constrained version that has infinite costs to the problem. And so if you were to, for example, take the minimum over x in 20.39, any solution to x that violates the constraint would never be would never be a minimum because you'd always get infinite. So right away you just satisfy the constraint. So it's an unconstrained version of the optimization problem. Now what we've done with the Lagrangian is take a soft constraint version. And you might think, well, doesn't that hurt us? Well, on one hand, the soft constraint version is always going to be a lower bound on a hard constraint version. And the reason why is because when lambda is greater than 0, so remember the lambda parameters are corresponding to the inequality constraints of the original primal problem. And the new Lagrange multipliers correspond to the equality constraints of the original primal problem. And so therefore, you have these two inequalities. I mean, the way you can sort of think of this, you can plot this even in some sense, is that, you know, this is sort of like infinity way up here. And then, and so you have the hard objective, which is this thing. And then the linear lower bound, which is this. Right? So it never reaches infinity, obviously. So when it's negative, this is going to be lower, and when it's positive, it's still going to be lower. And then similarly, for any value of nu, we have this. This is also satisfied down here because, again, when it's 0, when h is 0, whoops, there's a typo here. Anybody see the typo? This should be h. Make that typo correction. So when it's 0, we're going to get infinite. Sorry, we're going to get 0, but then h is 0, so it's an equality, and everywhere else it's a lower bound because the left-hand side is always real value. So therefore, we have for any value of lambda greater than 0 and nu, we have this inequality. Then also we have that opt is equal to the min over these of this hard constraint version of the Lagrangian. Sorry, excuse me. L box is the hard constraint version of the Lagrangian. And when we take the minimum over x, basically anything that doesn't violate, anything that violates the constraint is going to be infinite. Excuse me. Again. These will be sneezes that will go down in history, preserved for all eternity, for the rest of humankind. Because I'm posting this on YouTube. Everything I say will go down in history. Maybe people someday, 10,000 years from now, will be reviewing late 20th century. Is this still the late 20th century? Early 21st century information theory educational experiences, and we'll encounter this lecture and that sneeze. And maybe somebody will be studying like flus from the. I don't have the flu, by the way, but just the cold. But all sorts of things. Imagine what will happen in the future with all these YouTube videos. I don't know. I think something will someday happen very, very differently than what they're being used for currently today, I'm sure. That nobody will anticipate. But in any event, getting back to the material that we're attempting to learn, we have this expression, which is actually really important because it says basically for any lambda in nu. Let's start from this guy here and then move to the right first of all. Okay. First of all, for any lambda in nu, we have L, the Lagrangian at opt. For any lambda in nu, oh, this is not for any lambda. This is any lambda. This should be lambda greater than or equal to 0. We have this thing, which we saw before, and that's equal to the optimum value. But we also have this is the lower bound, right? Because for any given value of lambda and nu, when we take the inframinimum over x for a given value of lambda and nu, it might even be lower than the value of the Lagrangian might be lower than the optimum. Because those things are contributing to the value. Right? Those things can only be negative. Because in the Lagrangian form, we are not necessarily getting this infinite value here. Or I should say here. Here's another way maybe which will make it a little bit more sensible. Actually, it's on the next slide. But let's first of all define the dual optimal value. So we've got the dual function g. And we have lambda opt and v opt, which are basically members of this set. So it's members of the lambda greater than 0, new set, and define a dual optimal value d opt, which is g of lambda opt and d opt. So the weak duality, the notion of weak duality basically says that always, 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 we have that the dual opt is less than or equal to the primal opt. Now, if it's not clear to me why that's the case now, I think the next few equations will explain it to you. Let's take any value of x prime, lambda prime, and u prime. Any value. And look at this Lagrangian here. Because that's going to be less than or equal to the supremum over lambda greater than 0 and nu of the Lagrangian evaluated at that same value x prime. Because we're just taking the max, right? So any particular value is certainly going to be not any particular value here. It's not going to be lower value like this where you take the max. And this thing, moreover, is going to be less than or equal to L box. Right? Because L box basically says, well, if any of the constraints are violated, then you're going to get infinite. On the other hand, starting from, again, the Lagrangian here, again, for any value of x prime, lambda prime, nu prime, if we take the infimum, the minimum over x, that's always going to be a lower bound. So we've got the dual value at lambda prime, nu prime is upper bounded by this quantity here. Right, for any value of x lambda and nu, or x prime lambda nu prime. So then if we take the dual optimum, right? So the dual optimum, so this is now sort of using any value of lambda prime nu. The dual optimum is taking the supremum. So in some sense, this quantity here should be considered in relationship to here, and is equal to this thing here. Except that now we're optimizing over lambda prime. We're optimizing over lambda prime nu prime, so therefore we can just call them lambda and nu. And just by the definition of the dual opt, we said that that's equal to it. We're taking the supremum of the infimum. But now we're taking, on the right-hand side, we're taking the infimum of the supremum. Because this is true for any x, we can take the infimum of the supremum. And so we take the infimum over x, and we've got this guy. But that's going to equal to the infimum over x box, L of x box. Why is that? Let's look at it this way. Let's zoom in on this guy. Here. Let's take a particular value of x for a minute. Okay, for a particular value of x, if x is not feasible, okay, then when we take the supremum over lambda greater than 0 and nu, what we're going to do is be able to get infinity. Right? The reason why is, let's say that one of the h's, remember h is the inequality constraint, if h of I is not 0, and nu is unconstrained. So if hi is positive, we just make nu infinite. If hi is negative, we make nu negative infinite. And so therefore this whole right-hand side becomes infinite. On the other hand, if on the other hand, let's say that the fi's are not satisfied. So remember, the fi constraints, fi has to be less than or equal to 0. So if it's not feasible, then it says that fi of x is greater than 0. So if phi of x is greater than 0, and we're optimizing over lambda greater than 0, we just make lambda infinite. And so the right-hand side becomes infinite. So once we take the supremum of the Lagrangian, it essentially becomes like the box function. But then when we take the infimum over it, we would never ever take the infimum, we would never take the resulting infimum would never be one which gives this soup the opportunity to achieve infinity. The outer infimum never gives the opportunity for the inner supremum to achieve infinity. And so therefore, this whole expression is identical to the expression with L box, which is equal to, as we know, P opt. So duality, weak duality, then follows immediately from this. Dual opt is less than or equal to P opt, which is this expression. Okay. And we can also define, since this is true, we can always define the duality gap, and duality gap is never negative. It's never negative. And this is actually called the optimal duality gap, because it's the duality gap that's achieved at the optimal values of the primal and the dual. That's my cell phone. Anyone recognize that piece of music? No? Okay. No. It's a different topic altogether. Any questions? So, okay, duality gap. We understand that concept. Now, weak duality always holds. We haven't required the F's to be convex or the H's to be convex. We take the duality, G, the dual function is always concave. The supremum over the dual is always less than the optimum, irrespective of the convexity of the primal. Now, this notion of strong duality, and strong duality just means, when strong duality exists, it means that there's a zero duality gap. It means that P opt is equal to D opt. And we like strong duality very much. The strong duality is very nice to us. We enjoy strong duality's company. We invite strong duality to our parties. I would gladly seat strong duality in this class and go next door to get an extra table and chair for strong duality to sit, because strong duality always is nicely behaved and asks good questions and never makes a fuss. But really, why we like strong duality is because it helps us to solve problems. Because if it's the case that we have strong duality, we may, for example, come up with a candidate solution for the primal and a candidate solution for the dual problem. And even if it's not the case that we can guarantee that we can get the primal, we can actually look at the gap, the duality gap, or the current duality gap, and see how close we are to the optimal. And we can do that with weak duality too, but we know that with strong duality, it's possible to make this gap zero. And so we know when we've got the true optimum solution. If we optimize the dual and optimize the primal, and they're equal, or different by noise, epsilon noise, we know we've got the optimal solution. We can terminate. And oftentimes we can do early termination. If we know something about the objective functions, like let's say the objective functions are such that they're stepped in some sense, or they're in other words it's unlikely. Or let's say that we don't care too much about optimizing the objective function. Let's say we only care about optimizing the objective function to within epsilon of the true optimum. So if the primal and the dual are within epsilon, we know we've got it. We don't have to work anymore. And sometimes that can have an enormous speed up on real optimization problems. You just choose an epsilon. And if you choose epsilon 0, you spend there forever spinning and going through numerical difficulties. And as you all know, we're all dealing with IEEE floating point arithmetic, and IEEE floating point arithmetic often doesn't do very well when you're down in the noise. It sits there spinning, doing nothing forever. With epsilon, it stops before you reach that point. So strong duality allows us, it's sort of extraordinarily practical. Unfortunately, strong duality doesn't always hold. weak duality, while weak duality always does hold. So we care about conditions under which strong duality holds. Now, it's not absolutely necessary to have convexity for strong duality to hold, but it's oftentimes a condition for which strong duality does hold. So one condition that strong duality holds, there's a lot of ones that are discussed in Boyd's book, but there's lots of other books. I mean, there's a number of, you can go back to Rockefeller's book or a number of other books which identify conditions, sometimes in the convex case and sometimes in the non-convex case where strong duality holds. Convexity is almost always sufficient. One of the reasons why convex optimization is good is because it's rare for strong duality not to hold. So basically, Slater's condition is one sufficient condition for strong duality. It says that if f of I, if the f of i's are convex, then there exists a solution that's strictly feasible. So, namely, this is strictly true that f of I is strictly less than 0. As long as there's some x where f of I is strictly less than 0, then strong duality holds. And I guess this is in the case when h's are linear constraints. So we've got a set of convex constraints and a set of linear constraints h's. Then strong duality will hold. And that, by the way, happens to be in our problem, as we will see. Now, the other thing to note is that strong duality is useful to bound the gap in the quality of the solution. And the reason why is because, let's say here we've got a current x. So here's our current x here. and this is sort of how far we are from the true optimum. And this is upper bounded by this, for any values of lambda and nu. So if we show that this bit is small, then we're upper bounding how far we are to go. And again, this is this discussion, this point I already made about epsilon. If the upper bound is less than epsilon, we know that we're really less than epsilon away from the true optimum. So this thing here, this is sort of like the current duality gap at x. Right? It's not the optimal at x and lambda and nu. It's not the optimal duality gap, which is the one that is achieved when x is opt and lambda or lambda opt and nu opt. So then we can sort of plot this by saying, okay, well here's the values. These are the values of the solutions. These are the primal solutions, and we get x opt here. Against the dual solutions, we get d opts there. In this bit, in yellow, is the gap. Okay, which, like I said, in strong duality is 0. Any questions? Okay. So strong duality can be used as a stopping criterion for optimization procedure. And I've already said this. So if the gap is 0, we have the optimum. If not, we can compute absolute or relative error. You know, one thing we can do is, let's say we do early stopping. If we have a time constraint, we say, well, you have to do this, you have to solve this in 5 minutes. And strong duality says, well, I can not only solve this in 5 minutes, I can tell you how far away you are. At least I can upper bound how far away you are from the solution. Which is nice, it's more information. You might decide, okay, well 5 minutes is not enough. You might change other criteria. So now what we want to do is also be able to identify necessary conditions for optimality. Because sometimes if we identify necessary conditions, in other words, conditions that must be true when we're at the optimum solution, that can be sometimes good enough to actually help us to find the optimal solution. And this is this whole notion of Lagrange multipliers that you learn in your calculus class. And they just say, here's an optimization problem, form the Lagrangian, take Lagrange multipliers, take the derivative with respect to the x for giving Lagrange multipliers, plug that back into your thing, take another derivative, set it to 0, and boom, you've got your solution. And people say, well, why does that work? And nobody really knows why that works at that point. And the reason why it works is because of strong duality, because basically what we're doing is we're saying, well, these are conditions that are required. These are necessary conditions for optimality. And once we impart these necessary conditions, sometimes these are sufficient also. These constrain the solution enough with a little bit of additional algebra to actually find the solution. And that's what's happening for Lagrange multipliers. using strong duality. So here's a first set of necessary conditions. So let's derive the necessary conditions by first of all assuming strong duality, which we do here, and then looking at this series of inequalities. So we've got 20.48, which is basically this. Actually, I think in the next slide I have a step-by-step derivation of this, so maybe I might as well just use that. So let's go through it step by step. So this will be the same set of three equations. These equations will be repeated in the next slide. Here they are. So the first one, A, is, this follows from the definition, so this is A up here. Okay. So, oops, let's scratch. B follows due to the infimum and weak duality. So essentially, we're taking the lambda and nu are fixed. They're dual optimal values. And if we take the infimum over x, that's going to be less than the Lagrangian value, even at the optimum. Because it's possible, these things could essentially give you some sort of benefit or something. Could actually decrease the Lagrangian bit even more. So this therefore holds. And also, we also have weak duality.
Sorry, what do you mean by those that give you more benefit?
Well, remember, so this is the optimum solution here, right? And here we're just fixing the values of lambda, and we're taking the infimum over x for that particular set of values. And so therefore, this is the optimum of the actual constrained objective problem. This is the any optimum over x. Okay? So it's even possible that this, without ignoring strong duality, we just want to express this inequality here. This guy. It's possible this could, ignoring everything else, equation 2.52 could even be less than equation 2.54 because we know that lambda, it's dual optimal, and so therefore lambda I star is greater than 0. And f of I might or might not be. Right? So it could be that f of I becomes positive. The whole thing is that this thing is unconstrained. This is just the minimum of this expression for any given lambda and nu. For the given lambda star and nu star, whereas the second expression corresponds to the x being opt. Okay? Under the constraints.
So basically, you could like at x opt, you might not be minimizing the inequality constraints.
You might not have the constraints set. And here I think a better example is like looking at h. So we know that at optimal, x opt is primal feasible. Whereas when we do this minimum in equation 2.53, we might get an h which is negative, or this whole thing might be negative, which would make that smaller. But on the other hand, this whole thing is going to not matter because we're assuming strong duality. The second inequality we get, C follows because lambda I is greater than or equal to 0 because the lambda is dual optimal, and this again, the typo, this should really be star. Not a bad typo. And x opt is primal feasible, and h by optimal. So that therefore, but we have this whole thing. We have strong duality. Okay? So strong duality basically says, wait a second, everything's equal. So all these guys here, these are really equalities here. So what does that mean? Well, first of all, it means that we know that this whole thing is equal to 0, right? Because all the h's are equal to 0. But the other thing we know is that this whole thing has to be equal to 0 also. Because we're saying that this guy is equal to this guy. So this whole thing has to be equal. We're not saying that fi is equal to 0. We're not saying that the lambda I is equal to 0, but we're saying that that whole sum is equal to 0. The other thing we note is that each term in the sum, each one of these guys here, we know what? What do we know about that? That's right, they're less than or equal to 0. Because it's primal feasible, the f's are negative is 0, and then lambdas are greater than 0. So each one of these guys is 0. So we're summing up a bunch of negative values that equals 0. It's not really negative. It's a bunch of non-positive values that are equal to 0. So when we sum up a bunch of non-positive values, each one of them are non-positive, which is that bit, and each one, and the sum is equal to 0. So that must mean that each one of them individually is equal to 0. It's the only way to get that. Okay. So remember, these are necessary conditions for optimality, strong duality. This must be true. That must be true for all I. This stuff must be. The YouTube audience, I have to mark it. This is why I want to point it. That stuff here must be true. So, what does that mean then? Well, each one of those guys must be true. Necessary condition for optimality is either if lambda I star is greater than 0, so which, we're not saying that lambda I star has to absolutely be 0, but if it is greater than 0, then it must be true that this is equal to 0. If, on the other hand, this guy is strictly less than 0, then it puts a requirement on lambda I star being equal to 0. So this gets into this notion of active constraints. So either Fi is active, it's an active constraint, meaning it's in some sense actively constraining the solution by being equal to 0. Or if it's not active, meaning it's not actively constraining, we're not sort of at its boundary, then the lambda i's have to be equal to 0. Again, active means that it's sort of actively constraining the solution. So this gives us a set of conditions. Again, these are necessary conditions for optimality. Okay, so these are part of the KKT conditions, Hirsch-Kuhn-Tucker conditions. Conditions necessary, again, necessary conditions for optimality. I've said that a million times now. Now, furthermore, let's assume, this isn't always the case, but if things are particularly nice, then this is sort of getting back to our high school calculus classes where everything's differentiable. If everything's differentiable, and again we have strong duality, then all of these derivatives exist. Okay. So P opt is equal to this minimax optimization problem, right? Which is equal to min over x of L at the dual optimal solutions, right? So what that means then is that if we take the derivative of Lagrangian at x equal to x opt, lambda equal to lambda opt, and nu equal to nu opt, then that derivative is going to be equal to 0. So it's another necessary condition for optimality. So remember, like, when we just have an unconstrained optimization problem, a necessary condition for optimality is that the derivative is equal to 0. If it's a convex unconstrained optimization problem, we say, okay, the derivative is 0. That's a necessary condition for optimality. And then we take that derivative equal to 0, we solve it, and we get the solution. Right? If it's convex, we know there's a unique solution. If it's not convex, it's a necessary condition for being a local optima. We take the derivative set equal to 0, we get a local optima. Necessary condition. We're using the necessary conditions to give us a solution. What we're doing here is the same thing, except that we have a constrained optimization problem. We have a bit more. It's no longer a necessary condition for optimality that the objective that if we take the derivative with respect to x of f naught of x is 0 at the solution. That's not a necessary condition. But what is a solution is something that's very similar to that unconstrained condition, which is that at the Lagrangian evaluated at the primal and the dual optimal solutions, derivative must be 0 when we're at optimality. And again, since everything's convex, then we know that there's a unique solution. And so that gives us a way of characterizing the solution. So that set of necessary conditions. Right, so here's essentially a way of describing it. So this gives us this thing. Right? And that's again what we do. We use this. I mean, in the calculus classes, we say, well, take the derivative of the Lagrangian with respect to x and do this blah, blah, blah. Solve for lambda and do and plug it into the derivative expression and take the derivative. What we're doing is here, we're using this necessary condition for optimality, strong duality. We turn that back into an unconstrained concave optimization problem, take the derivative with respect to lambda and nu, find the maximum of the concave problem, we've got the solution. That's what we're doing in the high school calculus class. So here's the conditions summarized. So the conditions necessary for optimality, well, first of all, we have these guys. These are just feasibility. So the optimal solution has to, of course, be feasible. This also has to be true. Lambda has to be greater than 0. This is part of the KKP conditions that we derive based on strong duality. And this is the semantic Lagrangian derivative at optimality. 0. And it's often the case that with these conditions, that's sufficient. We can find a solution very easily analytically. Just plug these in, use these rules, conditions for optimality, plug them in, and get the solution. So, yep.
What are the conditions again under which you can do that?
Well, we need strong duality, we need convexity, and we need differentiability. We should add convexity. Add that to the title. I mean, in this particular case, it's Slater's condition, the energy is stronger than So I think this is the same slide, actually. I don't know why I have this here. But here's a summary of the slide we just saw. Why is this slide here? I don't know. And why is there no space between them? I should add some space here. There's no space here. Okay. Okay, so we've got 5 minutes left, and we have 5 minutes to actually solve our parallel channel problem. But let me, maybe more importantly, because I said I wanted everybody to really have a good intuitive and sense of duality. So people now, was this useful? Do you now have a good, strong sense of weak duality and a weak sense of strong duality? At least a strong sense of both weak and strong duality? What do you think? Do you feel more comfortable with it than you did before? I won't force you all 100% of you to answer. So what should we do? So let's go back to our original problem. So we have, we're trying to find the collection of powers to maximize the overall capacity, which is the sum of the individual capacity subject to this constraint. So you can see right here, again, that if we added additional constraints of the form like if we said like P I is less than or equal to P I max. If we added those kinds of constraints to get this kind of region, that wouldn't really change the problem too much. It's still inequality constraints. These are linear constraints, they're convex constraints. This problem turns out to be convex in P. P is what we're solving for. So it's a convex problem subject to convex constraints. And so adding these additional constraints, which you'd probably expect, like each individual power can't be above the P max. That's not going to change your problem too much. It's just going to add a couple of more Lagrangian multipliers. So we're not going to solve this problem, however. But we're not going to solve it with these additional constraints. But you should know that it's trivial. Clearly, it's trivial. It can be shown trivially to clearly show how it can be done trivially. Clearly. So now we're back to our Lagrangian, which is what we might have done had we not spent all of this time reveling in the theory of duality. So we have a vector of values. X is the variable that we're optimizing over. It's really just a vector of powers. N is the noises. These are constants. We're not optimizing over them. They're sort of fixed by the noise, the characteristics of the set of Gaussian channels that we've got. We used to call them sigma squares, but if they're n i's or sigma squared, it doesn't matter. We want to minimize. I mean, this is a maximization problem here, but we can just go ahead and minimize the negative of that thing. So actually, I guess this is really what I said before wasn't exactly correct. So this is really the convex problem. The above was a concave maximization. This is convex minimization. So I should have said that was concave. This is convex. Then we've got inequality constraints. We actually do have a couple of inequality constraints as well, which we didn't mention before. Well, we can't have negative powers. No problem. We can handle that. And so we can handle that with, for example, f of p is equaling negative pi. And we have an inequality constraint, which we can represent. This is an equality constraint with an h, which is equal to this quantity. Let's just zoom in on this. We can just say that this whole thing is equal to 0. So this quantity here, that's our h, which is equal to 0. So that's easy to do. The problem is convex. And moreover, I mean, there will be strictly feasible points. There's points that are strictly greater than 0, powers that are strictly greater than 0, and so therefore strong duality holds, as well as all of the KKT conditions necessary for optimality. So the way we solve it was we plug in these KKT conditions and do some algebra. And I don't think we're going to get a chance today to do that. So I think what I will do is stop now, and whenever it is, next Monday, we will actually solve this. And so all we're going to do is on Monday, we're going to start off with basically using the KKT conditions. These are, again, necessary conditions that are going to allow us, with some additional algebra, to find the optimal solution. And we're going to get the water filling bad. No, we're going to get the water filling picture, which is this. It's a world-renowned picture in information theory that everybody needs to know about if you're studying information theory. Okay, are there any last-minute questions? Any first-minute questions? Or mid-minute questions? If there are any questions, let me know, or you can email me. Okay, so I will see you on Monday.